Welcome back. So to this point, we have really only introduced three main varieties of first-order ODEs which we can actually solve. We had separable ODEs, which we solved by rearranging and then integrating both sides. We had linear ODEs, which we solved using integrating factors. And we have exact equations, which we found implicit solutions to using this technique from Calc 4 that we used for finding potential functions. In videos 10, 11, and 12, we're going to introduce some new varieties of first-order equations, which are not separable, not linear, and not exact, but which can be transformed into something that is linear or that is separable by means of a change of variable. What we're going to do is basically a u substitution where we're going to replace y with some other variable called u. And by doing that, we'll transform the equation into one that we can actually solve, and then we'll go back and we'll try and figure out what y was. In the first video of that flavor, we will be studying a variety of equation called homogeneous equation, which can be transformed by a change of variable into a separable equation. So if you have an ODE, specifically one which is in differential form, that ODE is said to be homogeneous of degree alpha if it satisfies the following property. If you go into the function called m and scale both x and y by some quantity, maybe call it t, then the result is going to be t to the alpha times the original function whose inputs were not scaled. The same thing must be true for the y component of this differential equation. If you scale the inputs, then that must correspond to a scaling of the outputs. The important thing in this expression is that both of these two exponents must be the same. Let me duck down to an example real quick just to show you what I mean. For example, in this ODE, we have mxy is equal to y squared minus y times x, and we have nxy is equal to x squared. So suppose that I go in to m of xy and I multiply the input x and the input y by a variable called t. Then instead of y squared, we now have ty squared. Instead of minus yx, we now have minus ty times tx. Now if I simplify this, I get t squared y squared minus t squared y times x, which is t squared times the original m of xy formula. Meanwhile, if I did the exact same thing to n of xy, if I go in and I scale both x and y by some quantity called t, then that x squared gets transformed into a tx quantity squared, which is t squared times x squared, which is t squared times the formula that I had at the start. So in both cases, I got t squared multiplied by the original function, which means that the differential equation in this example is homogeneous of degree 2. That is how we would check if a differential equation in differential form is homogeneous or not. Plug in tx for x and ty for y, simplify, and see if the result can be expressed as t to some power times your original function. If that can be done, and if you get the exact same power for both m and n, then your differential equation is considered homogeneous. Now when you have a homogeneous ODE, it may or may not actually be separable, but it can be transformed into a separable equation via the following change of variables. So here's the idea. Here's a four-step process that you can use to solve a differential equation if you find that it is homogeneous. The first thing that you want to do is you want to set an equation y equals u times x. We're going to introduce a new variable called u, which will be ultimately designed to replace the y's. If you apply product rule to this, then in the language of differentials, you can find the following result, that dy is equal to u times dx plus x times du. Basically, dx is taking the role of the derivative of the second, and du is taking the role of the derivative of u, just expressed in differential notation. So using the two results above, you want to go into your ODE and change variables from y to u. What this is going to mean is that you're going to want to go into the equation, replace all the y's with u times x, and replace the dy with u dx plus x du. Everywhere there was a y, there needs to be an expression containing u's instead. Now, if your equation really was homogeneous, and you did that check correctly, then after you do step 2, you should have a separable ODE. So you can use any of the techniques that we applied to separable ODEs to solve for u. And once you've found u, you can go back and express your solution in terms of the variable y using this equation y equals u times x. Let's apply that to the example ODE below. We already did the work and determined that this differential equation is homogeneous. In particular, it was homogeneous of degree 2. But regardless of the degree, we can do the change of variables in exactly the same way. We can set y equal to u times x, and dy equals u dx plus x du. Let's make those alterations in the ODE given below, and let's see what happens. So it's no longer going to be y squared, it's going to be quantity u times x squared. It's no longer going to be y times x, it's going to be ux times x. It's no longer going to be x squared dy, it's going to be x squared times x du plus u dx. So now that we've done the change of variable, let's go ahead and let's try and clean this up. This is going to be equal to u squared x squared minus ux squared times dx plus x cubed du plus ux squared dx. Now behold, we have here the term negative ux squared dx and the term positive ux squared dx. So if we combine those terms, they're going to cancel out. And we get u squared x squared dx plus x cubed du equals 0. Now let's go ahead and rearrange this so that we can solve it using integration. We get x cubed du is equal to negative u squared x squared dx. So u prime du over dx, would be equal to negative u to the minus 2 if I divide that over to the left side. And then on the right side, if I divide the x squareds, that would be equal to x to the negative 1. So truly it is separable. So let's integrate the left side with respect to u and the right side with respect to x. On the left, we get u to the negative 1, and on the right side, we get the absolute value of x, natural log, plus an unknown constant times c. Now if I want to actually find u, all I have to do is reciprocate both sides. U is equal to natural log absolute value of x plus an unknown constant. So I've changed variables from y to u. As a result of that, it became separable. And now I have found the solution in terms of u. It remains to find the solution in terms of y. So y is equal to u times x. I just found out what u is. In order to find y, all that I need to do is multiply this by an x. And here are our solutions. Let's do one more example. Solve the following ODE by any means. X plus y times dx plus x times dy equals 0. Now if you're on an exam or you're in the wild somewhere looking at an ODE, you don't really know at the beginning of the problem what method is best to use. And in certain situations, it's possible to use more than one method to solve an ODE. For example, here I can see at least two methods that would be viable. Method number 1 would be to use the change of variables trick that we just introduced in this section. Let's check to see if this differential equation is homogeneous. So our m of xy is equal to x plus y. And if I scale both the input and the output by t, then I get tx plus ty, which is equal to t times quantity x plus y, which is equal to t times mxy. If I do exactly the same check for n of xy, in this case just x, scale the x and the y by t, and you get t times x, which certainly is t times our original function. So this differential equation would be homogeneous, in particular of degree 1. So I could solve this using a change of variable. I could set y equal to ux, and replace dy with x du plus u dx. And let's see what happens if we do this. We get x plus u times x dx. We get x not times dy, but x times x du plus u dx equal to 0. And let's go ahead and simplify this. This would be equal to x plus ux dx plus x squared du plus u times x dx equals 0. Looks like we once again have some like terms here, plus ux dx plus ux dx, in total plus 2 times ux dx. So let's go ahead and let's simplify this. We have x squared du is equal to negative x plus 2ux dx. And notice that this expression on the right side can be factored. x squared du can be written as negative x times 1 plus 2u dx. So a little bit of rearranging, and we get u prime 1 over 1 plus 2u is equal to negative 1 over x. Integrating both sides, we get 1/2 natural log absolute value of 1 plus 2u equals negative natural log absolute value of x plus c. Or in other words, natural log of 1 plus 2u is equal to negative 2 natural log absolute value of x plus c. So 1 plus 2u must be equal to e times the entire expression on the right. And using the usual trick of turning the plus minus and the e to the c into a constant multiple k in the front. We can also simplify this exponential term. We can rewrite this as e to the natural log absolute value of x to the power minus 2, which can be rewritten as k divided by x squared. I've gone ahead and dropped the absolute value on x because once you square something, it becomes positive anyway, so the absolute value and the square are a little redundant. So that implies that u itself is equal to k divided by 2x squared minus 1 divided by 2. And since u times x is equal to y, this means y would be equal to this expression multiplied by x. K divided by 2 times a single x minus 1/2 times x in the numerator. But it's actually not the only way to solve that particular differential equation. Method 2 would be to say, didn't we just yesterday talk about how when you have a differential equation in differential form, if it's exact, there was a way to solve it in that case too? So method 2 would be, instead of checking whether it's homogeneous, to check if it's exact. So if our mxy is equal to x plus y, then the mixed partial would be equal to positive 1, and the mixed partial in the ends, and the mixed partial for n, the partial derivative with respect to x, would also be equal to 1. So that means that if we were going to give this solution implicitly, then we would start by integrating x plus y with respect to x. And we would get x squared plus xy plus some term containing y's and constants. Another representation of that same function could be found by integrating the n with respect to y. And that would be given by xy plus some term containing constants and x's. So if we match these two representations, x squared getting paired with c2 of x, and c1 of y being empty, because there are no purely y terms in the second representation, then we could find the following implicit solution. X squared, the x term, plus the mixed term xy is equal to a constant, maybe call it c. Now this is simple enough that it can be pretty easily solved for y. C take away x squared, then divide both sides by x. You get c over x minus x. And whoops, I'm just noticing now, right, that I forgot the over 2. And down here, this would be over 2. This would be over 2, and this would be over 2. Sorry about that. But with that correction, now we can see that the explicit solution found by this method is exactly the same thing as the explicit solution cooked up by the other method. There only appears to be a slight difference in notation. Here we have k over 2 divided by x, but in this representation, the k divided by 2 has just been combined into a refreshed constant called c. So do be on the lookout, especially with differential equations in differential form. We currently have two solution methods. One is to determine if it's homogeneous, and one is to determine if it's exact. I think that the exact solution, when possible, is much faster. This was only 1 page, whereas the other one I think was 2 pages. So I tend to prefer the exact solution method when it's possible. So that concludes today's material. We talked about what a homogeneous equation is and how to solve it by transforming it into a separable equation.